So here I am with explanation 6, and I will be I did some research on how active noise cancellation works in its relation to trigonometry. I'm going to be attempting to explain how these cancellation works with our trigonometric functions here. Okay, so I've done some research here, and a little example here is we actually measure our sound waves with sinusoidal graphs here. So we can actually take a sound wave from a specific note and actually put that in a function here. So this here, I did some research from on www.users.math.umn.edu, and they actually provided a great example here of a piano that when somebody plays a note A above middle C from a piano, we can actually take that specific note and put it in a trig function. It should be sine of 2 pi times 40x, or 440x. That would be our A note. Okay, so that's the example I'm using here, and the way these noise cancellation works is in modern headphones, there's a little microphone within those headphones that actually take the ambient noise, it measures it, and it spits back a reflection of that noise. So it tries to match, or it reflects the noise that's being analyzed, and it takes that same noise and reflects it right back, and it cancels out the noise. So I'm going to be explaining how that works here with these trig functions. Okay, so if we take this trig function here, right, sine 2 pi times 440x, and we measure it here. Okay, so we go up to 1 and it goes down, all right, to 0.002, it goes down with -1, it goes up. Well, this is supposed to hit 1 here. All right, there we go. This is supposed to go all the way up. All right, there we go. All right, if it goes all the way up, goes back down to hits 0.004, -1, bounces back up, goes to 0.005, and it keeps going. Okay, so if we want to take, if we take this noise, all right, and reflect it, all right, so pretty much we shift it a little bit, and that way the noise cancels out. All right, so we reflect that noise here. All right, so we take sine 2 pi times 440 times -x. Okay, we take the reflection of this, so now we're going down. So instead of, I'm starting, say we start here at 0. All right, and these graphs they go back, so they just I just didn't have much time to draw it, but anyway, so let's say we start from 0, go down to -1. So we graph this function here, down to -1, go up. All right, so we graph the reflection. We put a little negative reflection on the here. All right, so now we got two different sound waves. We have our original noise, and then the reflection of that noise. All right, so reflection, original, and the reflection, and we put them on the same graph here. Okay, I've color coded it. So blue is the original, and then the black is the reflected trig function. The trig function with the reflection. So we can see here, if they're both graphed separately on the same paper here, see, they kind of bounce off. So where the original one goes up, the reflective function or the function with a reflection, is reflected or mirrored across the y-axis here. Our original function. Alright, so why is this important? So let's say we added these two together. Alright, I mean, let's say we put 1 here, okay? So we took just 2 pi times 440x. Alright, so we take this, negative 1 times 440, we're taking this negative. Alright, so basically this is negative here, okay? It's positive. If we add these two together, alright, if we add these two together, they should cancel out. And I actually have a pulled up right here, a little example here that actually plays the note. Okay, so if we take this A note, all right, and we play it, okay, we take the reflected note, as you can see here, all right. But now let's say we play them both at the same time, so we add these two together. Nothing. See? So that's how, just a little simple explanation of how noise cancellation works using trigonometric functions.